Let's talk about L'Hopital's rule. So L'Hopital's rule applies to indeterminations that we find when we are computing a limit. And there are 4 types of indeterminations where we can use L'Hopital's rule. 0 divided by 0, infinity over infinity, negative infinity over infinity, R infinity divided by negative infinity. Okay, all these cases are indeterminations. So for example, let's say we have the limit as x tends to infinity of exponential of x divided by the exponential of x plus 1. This is one of these types, infinity over infinity. And we have already discussed some of these with algebra tricks. For example, in this case, we have learned that we can divide both numerator and denominator by the exponential of x. And transform the limit into something we can handle. So now would be 1 divided by 1 plus 1 divided by the exponential of x, which is the exponential of minus x. But now the exponential of minus x as x tends to infinity has a limit 0. So this is equal to 1 divided by 1, which is 1. So the indetermination infinity over infinity in this case resolves to a limit of 1. Another example, the limit as x tends to 1 of the logarithm of x divided by x minus 1. Again, this is an indetermination because we have 0 divided by 0. Well, in this case, we have a problem because there is no algebra trick that we can apply here. Okay. There is no algebraic manipulation that we can apply here. And it can get even worse. Okay, we can have something like the limit as x tends to 0 of the sine of x divided by x. Okay, this one is also an indetermination, 0 divided by 0 of, or we can have the cosine of x minus 1 divided by x, which is also 0 divided by 0. Okay, these limits actually, you could think, what are the chances that we run into one of these? These limits actually are very important because they appear in the definitions of the derivatives of the sine and the cosine. Okay, so if we write the definition of ddx of sine of x or ddx of cosine of x, we will find these limits. For example, ddx sine of x is the limit as x tends to 0 of sine of x minus sine of 0 divided by x minus 0, which is sine of 0 is 0. So this is the limit as x tends to 0 of the sine of x divided by x. Okay, so they are important. Now, these limits can be done geometrically. Okay, there is a geometric way. There is a geometric way to do these limits. You can see that in the book. So see the pages 199, 192. Okay. But the way we are going to learn is called the L'Hopital's rule. And actually, we will be able to solve many indeterminations that way. So this is very important. So let me call it a theorem. So suppose that the two situations where we can apply this, suppose that we have that the limit as x tends to a of f of x is 0 and the limit as x tends to a of g of x is 0, or situation 1, situation 2, the limit as x tends to a of f of x is plus or minus infinity, and the limit as x tends to a of g of x is plus or minus infinity. In both these cases, one or the other, but in either case, the limit as x tends to a of f of x divided by g of x equals the limit as x tends to a of f prime of x divided by g prime of x. This is L'Hopital's rule. Okay. I think I wrote one extra t. There we go. This guy, L'Hopital, was a French nobleman that was actually funding the research of Bernoulli. So this rule, actually, Bernoulli gave the name of the person that was paying for his research. So he was not actually a researcher. Anyway, let's apply this to some examples. So for example, we have a new tool. Let's apply it to some problem that we already know what the answer is to make sure it works. Okay, so this we have just seen, it's an indetermination. The limit we were able to show it was 1. But if we take the derivative of the exponential is itself, and then the derivative of the exponential of x plus 1 is also the exponential. So there is a cancellation, and the limit is 1, which is what we got before. So this looks good, looks promising. Now let me give you a warning, because it happens sometimes that we learn a new technique and we start applying it everywhere, even when we shouldn't. So make sure to check that you can apply the technique. Make sure to check that there is an indetermination of the four types. Whoops. Of the 4 types that we saw. Okay, 0 divided by 0, infinity over infinity, negative infinity over infinity, infinity over negative infinity. What do I mean by this? So for example, this I see every year, limit of x to negative infinity, the exponential of x divided by exponential of x plus 1, and people go ahead and apply L'Hopital here. And you can't apply it here because there is no indetermination. Because if you notice, the limit goes to negative infinity. So the exponential, as x goes to negative infinity, the limit is 0. And then in the denominator, we have 0 plus 1. So this is 0 divided by 1. And that is 0. There is no indetermination here. We are splitting 0 cake for one person. So that person gets nothing. Okay, no indetermination. So just make sure to check. Okay, don't go ahead and apply L'Hopital without checking. Now, more limits that we can do that we couldn't do before. So the limit as x tends to 0 of sine of x divided by x. Now this one becomes very easy because the derivative of the sine is the cosine and the derivative of x is 1. So the cosine of 0 is 1. So the limit is 1. Okay. We could also do the limit as x tends to 1 of the logarithm of x divided by x minus 1, right? That we saw this was 0 divided by 0. So we are good to apply L'Hopital. Okay, so this is the limit as x tends to 1 of the derivative of the logarithm 1 over x divided by the derivative of x minus 1, which is 1. So this is the limit of as x tends to 1 of 1 over x, and that is 1. More examples. Limit as x tends to infinity of the exponential of x divided by x squared. Here we have also an indetermination of the ones that we can solve using L'Hopital. Okay, so we have the limit as x tends to infinity of the exponential of x divided by 2x. And now we have here that this is infinity divided by infinity. Wait, what happened here? Well, we applied L'Hopital once. We got an indetermination of the same type. Let's apply it again. So the exponential, the derivative is ex again, and then the derivative of 2x is 2. But now it's clear. Now it's not an indetermination anymore. So this is infinity divided by 2, which is infinity. And here we have to apply it twice, but we should be patient sometimes because it may take several iterations. So for example, let's say that we want to find the limit as x tends to 0 of sine of x minus x divided by x to the power 3, which gives 0 divided by 0. It's an indetermination. So then we need to apply L'Hopital, right? So this is the limit as x tends to 0 of the cosine of x minus 1 divided by 3 x squared. And this still gives 0 divided by 0. So we need to apply it again. Take the derivative of the numerator divided by the derivative of the denominator. Okay. So the derivative of the cosine is minus the sine of x. The derivative of 1 is 0. And then the denominator, we have 6x. And we still get 0 divided by 0. So we need to keep going. Here, for as long as we get an indetermination of the types that we can apply L'Hopital, we just keep going. The derivative of the sine is the cosine, and then the derivative of 6x is 6. And here, the cosine of 0 is 1. So we get negative 1 over 6.